Why do fluids act strangely in space experiments? Imagine trying to pour water into a glass, but instead of flowing smoothly, it forms a floating bubble or drifts in strange shapes. That's what happens to fluids in space. When scientists conduct experiments on fluids in space, they see behaviors that are very different from what we're used to on Earth. The main reason is the environment called microgravity, where gravity is almost absent. On Earth, gravity pulls fluids downward, making them settle at the bottom of containers or flow in predictable ways. But in space, that pull is so weak that other forces take over. In space, liquids tend to form large, stable shapes that float freely. They don't settle into the bottom of a cup or drain out like they do here. Instead, they form blobs or bubbles that stay intact because of surface tension. Surface tension is the force that makes water droplets round and keeps them together. Without gravity pulling the liquid down, surface tension controls how the fluid looks and moves. This is why in space experiments, liquids can stay in a spherical shape or drift slowly through the air. The way fluids flow also changes in space. On Earth, gravity causes hot or cold fluids to rise or sink, helping with things like weather patterns or how your coffee cools. But in space, fluids move mainly because of surface tension, inertia, and viscosity. This means fluids spread out or drain at much slower rates, making their behavior easier to observe closely. For example, experiments on the International Space Station show that fluids spread out in a different way, called capillary action, over much larger distances than on Earth. Another interesting point is the shape of the meniscus, which is the curve where a liquid meets a solid surface. In space, tiny changes in the meniscus shape can cause waves or flow in unexpected ways. This is important for controlling liquids in spacecraft, like fuel tanks or water recycling systems. Small shifts in how the liquid's surface curves can affect how energy moves through the fluid, which is vital for keeping spacecraft systems working smoothly. Studying these strange behaviors helps engineers design better spacecraft systems. For example, understanding how liquids move in microgravity helps improve cooling systems and fuel management. It also helps scientists develop new ways to handle liquids in space, making future missions safer and more efficient. Plus, these experiments reveal fundamental physics that can be applied to industries on Earth, like manufacturing or medicine, where controlling fluids precisely is important. So, the reason fluids act so strangely in space is because microgravity removes the dominant force of gravity, leaving surface tension and other forces to shape how liquids behave. This leads to unique shapes, slower movements, and flow patterns that we don't see on Earth. These differences present both challenges and opportunities for space exploration and scientific research, helping us learn more about the physics of fluids and how to better manage them in space environments.